Hi there, today we'll be talking about enzymes, okay? And I'm not going to be going to the really highest level. I want to move this topic more towards a secondary level, as I think that's what most people need right now, okay? Enzymes is something very important to learn in biology, and it'll be used quite widely in the digestive system and other topics as well, okay? So enzymes, what are they? Enzymes are biological molecules made out of proteins found in the digestive system. Okay, that's where they can be found, but that's not where they are only found. They can be found at a lot of other places, and cells, most cells even contain their own enzymes. In the digestive system, you have saliva in the mouth, gastric juices in the stomach, and digestive juices in the small intestine. All these contain different enzymes. For example, the saliva in the mouth contains amylase, gastric juices contains pepsin, etc. So enzymes are responsible for catalyzing the breakdown of food into simpler substances. Make sure it's simpler substances because in digestion, you have breaking it into smaller pieces and simpler substances. If you have mechanical digestion, such as chewing, grinding, churning, those break it into smaller pieces or smaller substances. Whereas into simpler substances is digestion, chemical digestion, where enzymes actually have to work to break these large to make the food molecules, right? For example, fats from a fat molecule or lipid molecule, it will become glycerol and fatty acids. Enzymes remain unchanged at the end of the reaction. In a biological system, the catalytic function of an enzyme depends largely on its ability to bind to the substrate molecule, usually at one part of the molecule, and the binding site for the substrate is the active site. So basically, this active site, right, is over here at this part, right? And your substrate has to fit exactly, and that's why there are so many different enzymes tailored to different things because they have to be complementary. Oh, and a catalyst is something you only need very small amounts of energy to speed up the rate of reaction and lowers the activation energy, okay, allowing the reactions to occur faster. These are some factors affecting enzyme activity. So you have temperature, pH, so acidic value, this shouldn't be a capital H, P and small h. So this is acidic and alkali value, substrate concentration, and saturation of the active sites, okay? So first, temperature. Each enzyme has an optimum temperature at which the enzyme is able to catalyze reaction at its maximum rate. So for example, in this graph, this will be optimal temperature. Anything past that, it will drop again, yeah? So the rate of reaction increases as temperature is increased until optimum temperature is reached. This is the relationship. Beyond the optimum temperature, enzyme activity begins to fall as the enzymes becomes denatured. So what is the denaturing of enzymes? Well, the denaturing of enzymes is basically this process where the active site becomes not so complementary anymore. Now, substrate concentration. For a given enzyme concentration, the rate of reaction increases as the substrate concentration increases up to the optimal substrate concentration, after which the reaction remains constant, okay? At low concentrations, active sites are readily available for binding. So as substrate concentration increases, the rate of reaction increases. At very high concentrations, all active sites are saturated and can no longer accommodate additional substrate molecules. Therefore, it will remain constant, but it will not drop as the enzymes do not get denatured. pH. Okay, pH is very important for one part of the digestive system, which I'll explain later. So pH, they all have optimum pH at which they can catalyze reaction at its maximum rate. So for example, in this graph, it will be this. The values that are lower or higher than the optimal pH value can cause the site of the enzyme to be denatured. Why low or high can cause the site of the active site to be denatured? is because extremely acidic, we will just okay, for example, let's give an analogy, okay? You have this substance that you put it on a brick. You have a really strong acid, you have a really strong alkali. Both will be corrosive. Therefore, same for enzymes. Too acidic or too alkali is bad. Okay, unless of course it's tailored to work in specific conditions. Now, in the digestive system, you have your stomach, right? Which contains pepsin, which digests protein, right? So you have pepsin in the stomach, which is a type of protease. Protease digests protein, okay? And basically, the stomach also contains hydrochloric acid. So basically, yeah, digestive juices is hydrochloric acid plus pepsin. Now, the reason hydrochloric acid is there's two reasons. One, to kill bacteria and germs that enter the stomach. Yep. And secondly, is because hydrochloric acid, the low pH of hydrochloric acid is actually the optimum pH for this pepsin in the stomach to work. And that is why there's also a need for the hydrochloric acid to be in the stomach. Otherwise, this pepsin in your stomach will not work as well and digestion will not occur as smoothly. So optimal pH is actually very important for digestive system. For example, temperature. It's very hard to say that I'm going to increase the temperature of my digestive system as you have to heat up your body, or I'm going to decrease the temperature. It's much harder to regulate, as usually your body is at body temperature above 30 degrees. So pH will be the greatest variable. Protease in fruits. Protease are protein digesting enzymes. Okay, they break down proteins. They are also found in fruits enzymes. Okay, for example, this protease, okay, bromelain, is an enzyme found in usually pineapples. Okay, they can be used to tenderize meats, as they are able to catalyze the breakdown of protein structure called collagen, which shapes the muscle tissue. So this is actually something very interesting as well. If you have a steak, right? If you go online and you see, now there's this new method of cooking steak, where the way to tenderize it is they dip the steak and soak it in a pineapple. Yeah, pineapple, not a whole pineapple, as in a blended pineapple, so that the protease in the pineapple, the enzyme, will help break down some of the collagen, which gives shapes to the muscle tissue found inside the steak, making it more tender when they eat it. So this is actually very interesting cooking as well, and you can actually search that up online, right? It can also break down gelatin, which is found in like jelly, gummy bears. So technically, if you have jelly and gummy bears and you're planning on making some, you shouldn't put fresh pineapple on top because you'll make it liquidy. But what you can do is not use fresh pineapple but canned pineapple, because in the canning process, the pineapples are actually boiled, which brings me back to my temperature. When they are boiled, the enzymes are denatured. So the enzymes lose their ability to break down the gelatin. So if you're making gelatin or jelly, use canned pineapples, not fresh ones. Or you can just boil the fresh pineapple, that works too. Now, hydrogen peroxide in humans, plants, and yeasts. In the living cells of the body, hydrogen peroxide, H2O2, may be formed when some amino acids or fatty acids are broken down. Amino acids, fatty acids, yeah. Hydrogen peroxide is very toxic, and as it damages protein, DNA, and membranes. It may even cause cancer. So the cells in our body produces catalase, an enzyme that helps protect our body by breaking down hydrogen peroxide into water and oxygen. How to break down into water and oxygen? Simple. H2O2 will become H2O, water, and O, oxygen. Of course, it's not very balanced, so you have to balance it, but in the form of chemical reaction. But is still how it works. because it has to break it down, right? Okay, last part. I was mentioning digestive system, but enzymes, even though they are classified into from digestive system, enzymes will be classified into three main groups, right? Your carbohydrases, your proteases, and your lipases, right? They break down, well, actually you can see the S is plural, so the S at the back makes it plural, so because there's multiple. Carbohydrates, proteins, proteases, lipases, and fats, lipases. So yeah, they have their specific things to break down, and they're located at different parts of the digestive system as well. But there's also many different types of each. Okay, so first of all, carbohydrates. When you eat your starch, right, you have it's actually broken down by both amylase and maltase. Amylase is in the mouth, right? That's why if you chew your rice for a long period of time, it tastes sweet because the starch in the rice is broken down by the salivary amylase produced when you have saliva, and it becomes maltose, which is sweet. And when it goes down the digestive system, there's also maltase that breaks this maltose into glucose, which is the simplest form. It always aims to break it down to the simplest form in the digestive system for easier absorption of energy and nutrients. Proteases. So you have pepsin, tripepsin, and erepsin. So this is digestive system. I'm sure there are a lot more, but this is for digestive system. And your proteins are digested mostly in the stomach and small intestine or in the mouth, and they're broken down into amino acids. Okay, so you have your really long polypeptide chains. They're broken down into shorter polypeptides. Then the polypeptide bonds will be broken down into amino acids. This should all be covered in biological molecules. If I need to cover that, I'll cover that in the future. Lastly, we have lipases and fats, which will be broken down into fatty acids plus glycerol, which is what they are formed of. I should draw them. Glucose is actually, so my drawing is not so good because my control is also not so good. But that's usually the structure. Amino acids will usually come in all shapes and sizes, right? And fatty acids plus glycerol will usually look like sort of a jellyfish thing. Yeah, I mean, well, let me try. Yeah, sort of like that. I know my drawing's quite ugly, but yeah, basically. Oh, and to note, lipases, okay, in digestive system, right now we only need to learn lipase, okay? Bile is not an enzyme. The bile is stored in the gallbladder produced by the liver, right? It's not an enzyme because it does not actually break it down into, it doesn't carry out chemical digestion, it carries out physical digestion, mechanical digestion or physical digestion, and it usually occurs in the small intestine. Okay, bile contains these bile salts, which emulsifies the large fat molecules and breaks them into smaller fat molecules. When they're smaller, there's more surface area for the lipase to work on. So it's not an enzyme because it's from big to small. It doesn't become fatty acids plus glycerol. It's just a big fat molecule becomes smaller fat molecules. Therefore, bile is not an enzyme, which is a common misconception in the digestive system, right? So yeah, I've covered enzymes, but enzymes usually is not a standalone topic. Enzymes will usually be more under the digestive system, and it's something we have to know for a digestive system. But enzymes itself is quite interesting, as usually all these should be known, but there are a lot of misconceptions in enzymes. For example, denaturing. Denaturing does explain a lot, okay? pH also. So yeah. Oh, and another misconception, alkali is not always better. Sometimes you need it to be acidic for it to be optimum pH. Not always alkali is good because we are always trained to think acids are bad, alkalis are good, but that's not true. It usually depends on the situation. Okay, but that's all I have to cover for today. Thanks for listening.